Thank you. So I have to admit that I'm a local, so for me it was a drive down here, which is nice. And it's funny to see all of these things going on, what you can do when climate is not really getting in your way of life. You can do topiaries, you can do yeast tasting in beer, you can surf. It's nice being here. The one question I want to ask the crowd is how many people here think that it's cold outside if you're from Texas and it's pleasantly nice and not 1,000 degrees? And how many people are from northern climates where you think it's warm outside? It's one of those three bears things, right? I came here enough times to think it's just right, so I'm moving here. So I'm going to talk a bit about HPC. As many of you probably know, ARM is starting to make inroads into high-performance computing. It matches with my background. There is a huge amount of leverage going on in what we're doing in high-performance computing, huge. And we're standing on the backs of giants. We're literally taking advantage of much of the work that you're doing here to elevate us in high-performance computing and let us attack some of the world's toughest problems. And as hopefully I'll get across in this talk, some of the new architectures that are coming our way on the internet. HPC is generally thought of as pushing boundaries. HPC is a really good community to engage with when you have a new technology. The community is exceptionally tolerant of stuff that almost works but doesn't quite. You got to kind of stand like this to make it work. The community that I come from is really good at being able to make use of early stage products, and I'll show you a couple of slides as to what's been going on there. My background, I started doing high-performance computing in the mid-'80s in Canada. I'm actually an immigrant. I like to tell folks that I'm an environmental refugee moving from the prairies of Canada where it was 40 below to San Diego where below doesn't actually come about. I've spent about 15 years in the US National Laboratories, mostly Lawrence Livermore National Laboratory, but the Office of Science Laboratories as well. I was responsible at Livermore for an architecture called the Blue Gene architecture, which was a project with IBM in the early 2000s where we took, at the time, Beowulf clusters were growing to be on the order of 10,000 nodes, and we took that and scaled it up to 150,000 nodes with 6 million way parallelism, that sort of thing. If you were here for Satoshi's talk yesterday, he mentioned that their machine has more nodes than Blue Gene, and that's what he was referring to. The Fugaku machine has 7.5 million cores in it. Imagine writing an application that harnesses the power of 7.5 million processes at the same time. Pretty quick, you run into an issue called Amdahl's law, where any serialization in your program means 7.5 million minus 1 are sitting idle. And so it takes a lot of heroic effort to make use of these systems. I'm going to try and pull that back and show you where I think AI is going, where I think HPC is going. I need to find a mouse here. There we go. And I want to talk about HPC as an architecture, separating it from HPC as a workload. In HPC, we get to talk about big science all the time. Satoshi actually had a better picture yesterday about doing drug discovery in molecules and so on. This one is important because it's actually running on ARM silicon in Bristol in the United Kingdom on a system called Isambard that I will show you a little bit later. Researchers there a month ago had not yet published the paper, but they were on the verge of publishing a paper about new discoveries with respect to Parkinson's disease on the left, and in treating osteoporosis, which is a bone density issue, on the right. So today, even though I claim that we're early on in HPC, there's real science being done at scale. That image on the right took 1 million core hours to simulate. Okay, so this is the standard things you think about for HPC. One of the projects going on at Bristol is this jet engine project, and it's got a name, if I can find it here, Asimov that they are doing with Rolls-Royce. And I spent some time at Rolls-Royce talking with them about this. But this is your standard heavy-duty HPC simulation that has multi-physics with fluid dynamics and heat diffusion and electromagnetics and all of that coupled into a single application. And of course, the goal there is to try to digitally create a jet engine that is more efficient on fuel, less sound, more carrying capability, that sort of thing. This particular simulation is going to require an exascale of performance in order to be able to run it. So this animation is not yet a fully operational multi-physics package. So we talk a lot about HPC, and again, we tend to overemphasize the high end of HPC. And Satoshi yesterday actually compared his machine, this new Fugaku machine, to all of the cell phones sold in Japan. That machine is as capable as, I think he said, 1 million cell phones, or maybe 10 million. So all the cell phones sold in Japan. I think lots of people don't get the scale of this, though. In the early 90s, I was at the Lawrence Livermore lab, and I was given the responsibility of touring senators through our machine room. And you can imagine that senators don't know a whole lot about computers. Questions would be, I thought computers were getting smaller, not bigger. And we'd show them, here's where the new computer's going, and it's going to be this big and that wide. And they'd go, I thought computers were getting smaller, not bigger. So I worked up an analogy that seemed to resonate with them. This is a picture of Lake Tahoe that I took this summer. Lake Tahoe holds about 40 trillion gallons of water, more or less, 10 to the 12th. In 2002, Japan with NEC released a system called the Earth Simulator that was roughly capable of 40 teraflops, which is roughly about one floating point, 64-bit floating point operation for every gallon of water in Lake Tahoe for every second. So if you've ever been to Lake Tahoe, 72 miles around, about 100 kilometers around, and it's one of the deepest alpine lakes in the country. That is kind of order of magnitude where we were close to 20 years ago. In 2008, we hit the petaflop scale. And to put it in perspective, the Great Lakes hold about 6.5 petaflops worth of water. So again, 15 years ago, the capability of the high end of these systems was one 64-bit operation for every gallon of water in the Great Lakes. And of course, we've dramatically increased that over time. This is a picture that those of us in high-performance computing like to trot out. This is the top 500 list for the past 25 years. The red line in the middle, where it says n equals 1, that's the world's fastest machine at any given time. The list comes out twice a year, November and June. And the orange list, the orange line below it is what it takes to get on the top 500. So it's machine number 500. And then the summation of all the machines are what you see at the top line. So currently, the systems are such that it takes a petaflop of performance to get on the top 500. The top machine, which is at Oak Ridge National Laboratories, an IBM system with Power CPUs and NVIDIA GPUs, is at 150 petaflops. And then the entire summation of the top 500 is just over an exaflop and a half. Exascale computing is kind of where the target is right now. So I want to point out a couple of interesting aspects here. The Earth Simulator, that machine that was capable of one floating point operation for every gallon of water in Lake Tahoe, came out in 2002. And you'll notice that there's a bit of a step up in the number one graph. High-performance computing has been quite political for a long while, and it's getting more so. When the Japanese released that Earth Simulator, it made the front page of the Wall Street Journal, and there was a whole race on with respect to, similar to an arms race, there was this talk of ComputeNIC and how the US is losing its footing and no longer the world leader, that sort of thing. So you'll notice in here that there's kind of step functions going along where there's a breakthrough You'll have a horizontal line where the systems seem to stagnate for a bit and then there's a breakthrough. Without stealing Satoshi's thunder, I would expect that there's going to be a nice little kick up for him coming in the near future. The first petascale machine was an interesting architecture. It was at Los Alamos National Laboratory. It was called Roadrunner. It was actually done with the IBM Cell processor, which is, if you have kids, you'll notice that that's the same that's in the game station back then. And it was 138,000 cores, so it was quite a big system. And it was mostly a detached architecture in the sense that you had these cell processors that were quite a distant from the CPU, and programming them meant shuffling data back and forth and getting into algorithms that can overlap the computation with the shuffling of the data, and it turned out to be quite difficult to program. I will add in here, just out of interest, there was a machine in '09 from AMD that is called Jaguar, and the reason it's interesting is because 10 years ago it was the #1 system on the top 500, and this year ARM's first entry on the top 500 is a system called Astra, which is at the Sandia National Laboratory in Albuquerque. 10 years ago it would have been #1. Now it is number 156. So if you take a look at my cartoon, the tip of the arrow there, the distance from that to the red square, that big distance, there's only 150 systems there. But the distance from the tip of the red arrow down to the orange line, there's 350 systems there. So this pyramid is very flat shaped. We always talk about the top 10 and the top 100 and so on, but it's very flat shaped. And of course, these are the systems that are spoken about publicly. There's a lot of systems that go into environments where they're not talked about. And I don't mean by that classified government environments. There is a bit of that, but there's a lot of commercial competition these days where an oil company or a bank will buy a very big system and then they won't report it out to anybody because computational capability is really a commercial advantage if you know how to take advantage of it. And that's kind of where we're coming in. So I want to underscore that these processors are not embedded processors, right? These are first-class citizens. This is a year old now, which in HPC is ancient. But a year ago, Bristol released these performance numbers where the ARM system, which is from Marvell, the ThunderX2, are the green bars. And it's showing a socket-to-socket comparison, performance-wise, how it compares with the x86 state-of-the-art at the time. So socket per socket, the ThunderX2 is outperforming Xeon processors there. But we do start with embedded processors. A lot of our HPC capability in ARM can be pointed back to the Montblanc Project in Europe. So Europe is really a leader with respect to getting us into this market. Europe represents about a quarter of the HPC market worldwide. The US is about half, and Asia is about another quarter, roughly speaking, for where the dollars flow. But Europe is definitely a leader when it comes to trying out the new architectures. So there's been 3 rounds of the Montblanc project with hardware in each one, and of course, raising capabilities and software ecosystems to come along with that. Recently, with the help of Hewlett-Packard, 3 systems were installed in around the beginning of the year in the UK at 3 different universities. And these are 3 systems that are intended to help elevate the infrastructure and the applications programming capabilities on parallel systems based on ARM servers. They're all Marvell ThunderX2 based systems. They're all from HPE. They all have interconnects from Mellanox. They all run SUSE as an operating system. So there's a lot of interesting work going on there. More public and more leadership oriented than we see in the US. Those are systems from HPE. Cray also builds systems, and if you're paying attention, yesterday the acquisition closed. Now HPE owns Cray, so now they're one and the same. But Cray also has installed ThunderX2 based computers around the world, and this is one that is The one that I mentioned earlier with the drug discovery algorithms running on it and the jet engine applications starting to come up on it, and that's in Bristol. And this is the current largest public ARM system in the world, again based on the ThunderX2 processor. So this is the one that's at Sandia National Lab in Albuquerque. Okay, a couple of shifts. The first thing is I mentioned that HPC is political. There are 4 very strong thrusts towards the exascale capability platform. They are going on in the US, in the EU, in China, and in Japan. Yesterday we learned a lot about the architecture going on in Japan. That system is imminent. They talk about having access to hardware now. Satoshi will talk about the ARM server-ready program that permits him to boot Windows on his big system. He even mentioned that yesterday, that he would be able to boot Windows. I don't know how Windows runs on 7.5 million cores, whether it's, anyway, I'm a BSD or Linux guy, but that system is going to be next out of the gate. One of the great things about the ARM business model is that partners can take the core IP and build that into what they want, and that's really foundational with respect to our interest in high-performance computing. I will talk a little bit about the EU activities. You'll see all the data here. I don't need to read it for you, but the EU is going down a path of an ARM-based system with an accelerator with it. China's interesting because they have 3 different projects betting on 3 different pieces of silicon, one of those ARM-based. And then the US is, I think, the most interesting because there was an x86 solution that was supposed to show up in 2018 and hasn't shown up yet. And the vendor is in the doghouse a little bit with respect to not delivering on that contract. These contracts, by the way, are hundreds of millions of dollars. It's probably got a dollar sign up by the Japanese target, but that was $1 billion investment to get that machine stood up. So the US will be interesting to follow, very interesting to follow. It's going to get hot and heavy in here soon. A few things about the Fujitsu machine. It was called the Post-K machine forever. It was 10 years in the making, just like the Earth simulator was 10 years in the making. We should not have been blindsided by that 40 teraflop system because the Japanese were very public saying, we're building this system, we're building this system. When they turned it on and ran it, we all went, oh my God, they built the system. Makes no sense. They told us they were building the system, and they did it. And so they're doing that again with the A64FX processor. So 10 years is a long time, but what they do in that 10 years is they dissect their algorithms. They know what they want to implement. They know how efficiently it needs to run. They know everything about the energy costs. They know everything about the software environment. By the time that machine is plugged in and turned on, it runs like a Toyota, right? It just starts up and goes. Some amazing performance numbers that they're coming out of that. The other thing that I wanted to point out, 2 more things, I guess. Satoshi yesterday said that this system has more bandwidth by an order of magnitude than all public cloud infrastructure today, by an order of magnitude. 8 years ago, he was at Tokyo Tech, and he stood up an HP system, and he wrote a paper that showed that that system had more bandwidth internally than the entire internet. Okay, so those are some big numbers. In high-performance computing, we are not scared of putting together millions of devices and making things work. And Satoshi is one of the world leaders in that. The other thing to point out is that I don't know that he mentioned it yesterday, other than he was talking about his facility. They turned off the K machine so that they can ready the facility for the post-K machine. One of the subtleties in there is they have plumbed 10 or 15 megawatts to that building. That's nowhere near enough for this new computer. This new computer is 40 megawatts. So part of their upgrading the building is to redo all of the electrical to take it up to 40 megawatts. when I was at Livermore, we stood up a building with 15 megawatts of power. And when I forked off a company to go do my own thing, they about doubled that and took it up to 35 megawatts. And everybody said, that's the ceiling, it ain't going any bigger than that. Well, 3 years ago, they took it to 60, and now they're taking it to 80 megawatts. So the lesson here is that electricity is one of the biggest components of these systems. What does ARM offer in this, right? ARM's background is performance challenged in an electrically restricted environment, right? So the designs that are in this community are very much anticipated and sought after by high performance computing. When we talk about electricity, the rule of thumb is it's $1 million per year for every megawatt. So Livermore is biting off on $80 million a year just to power the machine. Whether or not it's running an application, it's going to cost them $80 million. That's a big number, right? That's a big number in any budget. Okay, the next exascale project that is to watch closely is the European project. And these folks have the difficult task of bringing 25 countries together with different cultures and different languages and negotiating together to come up with an indigenous design for a processor. There's the obvious political undertones of that, but the more subtle piece here is the driver for them is to be in charge of their own future. If you roll the world forward and politics get to a point where countries restrict other countries from having access to technology, you really want to be in charge of your own IP and your own technology. So HPC, again, is an area that you have to tread carefully and you have to be very specific about what you're working on. So that's another project that's going to be super interesting to watch. I'm going to switch gears a couple more times on you. The next one is the HPC Software Ecosystem. ARM is really, really good at standards, really, really good at open source, and really good at partnering with people. About 3 years ago, ARM bought Alinea, which is a compiler tools group in the UK, and that forms a lot of the basis for how software comes together inside the company. But it is not lost on anyone inside ARM that a lot of the software comes from the community, and we really appreciate that. There'd be no way we'd be in this market without Red Hat and SUSE and on and on and on porting to the ARM system. We all believe competition is good. Having competition to x86 is very good, and we all understand what it takes to get there. Right now, one of the biggest poles in the tent is having to do with porting of applications and with ISV codes. We run into a number of situations where we go in to talk to an end user site and they want to have the PAM crash codes, they want to have all these different ISV codes available to them. So my ask to this audience, if you deal with the ISVs or you're at an ISV, we are super interested in helping you with that port, helping you find the customers, helping you find the early users. There's only 2 of us in HPC business at ARM, myself and Darren Cephalus, but we will take the time to meet with you and try to help prime the pump for those ISVs because they will turn into downstream activity for ARM. A little bit of motherhood and apple pie here. ARM shipped 21 billion chips. ARM doesn't ship any chips, right? I get a real kick out of all the people that say, that's an ARM HPC system. Well, it's really a HPE system based on Marvell products, but if you want to give me the credit, that's great. I'm in management, I know how to take credit, no problem at all. ARM is really, really solid in the embedded space, right? In the handheld space, all that sort of thing. The servers are where I'm spending my time. And I'm particularly focused on HPC, which is my background for 30 years, but also how that bleeds into the server space. Because HPC on its own does not generally constitute a market. But HPC is a huge, good partner, like I said earlier. HPC will work with you, it will fund you, it will get you up on that surfboard, but you got to have your eye on that next wave when you're doing it. So if you've seen any of the public talks lately, we've got a new brand called NeoVerse. And a quick summary of that is that the NeoVerse brand is everything to the left of Cortex, where Cortex is all the embedded and handheld stuff. NeoVerse is meant to cover the fog, the data center, networking, storage, all of that sort of thing. And it was announced at TechCon almost exactly a year ago. And the argument that we make here is that with the explosion of IoT, the data flow on the internet is about to turn around. Right now, the internet exists to send you cat videos that you watch on your cell phone, right? Pretty soon, you're going to find that 1 trillion devices, order of magnitude in the field, are all trying to send data to the left in this picture, upstream to the cloud. And there's a whole lot of activity going on as to how to do data reductions. You know, in the past, there's companies that have done content distribution. Now we're doing content reduction talks. And my alter ego here is that I've done a number of startups, and I've hung out with VCs and so on. And so I get to talk with startups about ideas in this space. And there's really some great ideas coming here. The one from an HPC perspective that I want to point out to you is in thinking about that wider base of HPC, not the top 100 or even the top 500, we are going to be seeing HPC-like activities moving out to the edge for latency purposes, for data movement purposes, for running algorithms that can do prediction better than your phone can do. There's a huge amount of opportunity in that space right now. So watch that space for these sorts of hardware devices and applications. The broad envelope here that you should be paying attention to is with a consistent ISA from the edge to the data center, you have opportunities to think about where that workflow runs and migrating that workflow closer to the edge and back to the data center. HPC is going to, the big HPC is going to remain in the data center and be the heavy duty bulk thing. But the concepts that we're coming up with are going to be pushing down towards the edge as the data is pushing up towards the edge. So it's really an interesting time to be working here. I think I will skip the argument HPC is an architecture versus a workload. The simulation workloads are what everybody sees by HPC, but there's a whole lot more there, and I want you to pay attention to it. And then I will just close by pointing out that we're very data-driven here. The Economist published that, Chips Everywhere, about 2 or 3 weeks ago, and they are starting to get on the bandwagon of there's going to be IoT everywhere, and there's all sorts of issues with it. There's all sorts of opportunity with it as well. But believe it or not, I ran into this CIO review just surfing the net the other day. I wasn't aware that our CEO was on the front page of CIO review talking about supercomputing. When I got up here, remember I said I own supercomputing at ARM? You'd think I would know about being on the cover of something, but I didn't. So, thank you for your time, and enjoy the rest of your event. Questions?
So I do have one question, and that
surfing or Ho Chi Minh.
So yesterday, Matoka Sensei basically explained how they had the ceremony to shut down the K, and I sort of in my mind had that picture from 2001 when Dave is shutting down HAL, right, in the spaceship. But why shut it down? Is it that it's just not useful anymore? I mean, I know they needed the space, but they could build a new building. Is it the cost of the electricity to run it isn't worth it anymore?
It's effectively that latter bit. Think about where he's going. He's increasing his capability by 2 orders of magnitude for about double the cost of the electricity, right? So those two numbers together mean that the old hardware to him and his facility is not worth it. To somebody else, that hardware has value. So to pull another random example out of the air, Texas Advanced Computing Center goes through a lot of big computers. They turned off one of their systems a couple years ago and they shipped it to Portugal. And Portugal stood up a supercomputer because to them, the cost of electricity wasn't as prohibitive as the acquisition cost. And if you can get it for free, the shipping cost, then we've got some capability that we can start to prime the pump with.
So K will go somewhere. There's a second-hand market for HPCs.
It may, I don't know. I haven't talked to him about that. There's some interesting stories about a second-hand market for old Crays that, beer would get some pretty funny stories out of me with that because they have gold leads in them. And so people will buy them for the precious metals.
Thanks so much for joining us today. I really appreciate it. Very interesting. And now